Alrighty, hello and welcome to lecture. We are going to continue with our discussion of chapter 4. We will probably be finishing it off tonight. We'll see how lecture goes. So yeah, let's go ahead and dive right in. So before we jump into new material, I just want to do a few more examples with Lewis structures. Just because this is it's a very important thing. It's something that you definitely want to nail. So I'm just gonna just do a few more examples, and then we'll jump into the last couple sections of chapter 4. So our first example is draw the Lewis structure for excuse me, for, let's see, what would be a good PO2, the charge of -1. All right, now first step is we need to total our electrons. All right, we need to count up how many electrons we have to spend. Phosphorus, if you look it up on the periodic table, it is in the 5th column of the main group, so there are 5 valence electrons. Oxygen has 6, but because we have 2 of them, 2 oxygens in play, together they'll bring a total of 12 valence electrons. And then our negative charge means that there's 1 extra electron, 1 more electron than there would normally be in this molecule. So we have to, because we have a -1 charge, add 1 more electron to this molecule, giving us a total electron budget of 18. All right, now, when it comes to picking which element is our central atom, phosphorus is on the 3rd period. And we know that anything that's on the 3rd period or lower is capable of breaking the octet rule, so it can make more than just 4 bonds. So, we're going to select phosphorus as our central atom. Now, our first move, or I should say our next move, after selecting our central atom, is we need to connect all other atoms to our central atom. So we've got 2 oxygens. We need to attach both of these oxygens to phosphorus. That is going to cost us 4 electrons total. Right, 2 per bond. So now we have 14 electrons. All right, next we need to start completing our octets. Now, I'm just going to start with oxygen. Our first oxygen has 2 electrons as currently drawn, I should say, access to 2 electrons in that bond. It needs a total of 8, so we need to give it 6 more electrons. We have it in the budget. So 1, 2, 3, 4, 5, 6. 14 minus 6 leaves us with 8 electrons in the budget. Our second oxygen has access to 2 electrons. It also needs a total of 8. So we need to give it 6 more. 1, 2, 3, 4, 5, 6. And we have 6 electrons in our budget as well. Now we have 2. We have 2 electrons left, so we can only give phosphorus 2 electrons at this point. Now we're out. None left. All right, none left. But phosphorus does not have a full octet. If you look, phosphorus right now has 2 electrons per bond, right? So it has, if we look at phosphorus, it has we've got bonds and we have lone pairs. And right now we have 4 electrons from bonds and we have 2 electrons from lone pairs. So phosphorus right now only has 6 electrons and it needs 8. We don't have any more electrons in our budget, so we can't give it another lone pair. And this is the situation. We said we talked about this on Thursday, or Tuesday actually, sorry. That whenever you're down 2 electrons, the way you recover, the way you give everybody a complete octet is you need to make a double bond. You need to make a multiple bond. So it doesn't matter which oxygen you take from, but you need to take 2 electrons away from one of your oxygens and use it to make a double bond to phosphorus. So this is the Lewis structure for phosphorus. Now, yep, Rox, that is exactly correct. And the last step, because we're dealing with an ion, is we have to throw a bracket around the molecule. And whatever our ionic charge is, in this case, it's -1, we need to put that charge superscripted to the right outside the bracket. So this is the Lewis structure for the ion we were asked to draw. All right, let's maybe do one more. All right, let's draw the Lewis structure for, I'm going to take a look at the periodic table. Rox, that is a great question. You can totally just leave the negative sign because it's -1. If it were -2, you'd have to put -2, but for -1, you're totally fine. Just leaving the negative sign. Let's draw the Lewis structure for SiO3 with a -2 charge. All right, now first order of business is we need to total our electrons. Silicon is in the 4th column of the main group, so it has 4 valence electrons. Oxygen, as we know, is in the 6th column, but because we have 3 oxygens in play, they're going to bring a total of 6 times 3, which is 18. And we have a total charge of -2. So that means we have 2 extra electrons to spend. So let's go ahead and add those to our total count, giving us a budget of 24 electrons. All right. Now, again, just like the previous example, we have here a 3rd period element, silicon, so it is capable of breaking the octet rule. We're going to select it as our central atom. Our next move, we need to attach all our other atoms to our central atom. This is going to cost us 2, 4, 6 electrons. All right, 24 minus 6 is 18. 18 electrons left in our budget. Now we need to start rounding out our octets. So our first oxygen, all of our oxygens, this is true, right? They have access to 2 electrons as drawn. And they need a total of 8, so we need to spend 6. After giving our first oxygen 6 electrons, we will have 12 left in our budget. Our next oxygen also needs 6. We have 6 to spend. We have 12 to spend, actually. Leaving us with 6. And our final oxygen has 2 electrons. It needs a total of 8. So we will spend our final 6 on that last oxygen. Silicon, as drawn, only has it has 3 bonds, so it has access to 6 electrons. It needs to have 8. So when you're 2 electrons short, you remove a lone pair, make a double bond. Because again, we're dealing with an ion, we put our Lewis structure in brackets, and we write the charge superscripted to the right of the bracket, and that is the Lewis structure for silicon. All right. So that is, those were just 2 reviews to kind of refresh our memory. It's been a little bit since we've been in lecture, right? There was an exam, so I just kind of wanted to refresh all of our memories before diving into new material. Now, the next topic that we're going to discuss is related to Lewis structures, but it kind of gets at what one of the real downsides that Lewis theory has. So, for example, let's draw the Lewis structure for water. All right, kind of going back to one of our early problems. Now, when you draw the Lewis structure for water, you might end up with a structure that looks like this. Or you might end up with a structure that looks like so. You might also get this as your Lewis structure for water. Or, fourth and final option, your Lewis structure for water might come out looking like this. All right? And the answer to the question, well, which is correct, is all of these are correct. It does not matter how you draw it. In all of these, oxygen has a full octet. In each Lewis structure, it has 2 single bonds to hydrogens and 2 lone pairs. Each hydrogen has 1 single bond. So they're all equally correct. And this is what I want to stress. They're all equally correct because Lewis structures do not represent molecular shape. All of these are correct because the Lewis structure of the molecule does not accurately represent the molecule shape. Now you might be going, well, what do you mean it doesn't represent the shape? We're drawing structures, we're drawing molecules here. Like, what do you mean it doesn't represent the molecular shape? And here's what I mean. A Lewis structure tells you something very specific. A Lewis structure tells you connectivity. All right? It tells you how the molecule is connected. What it does not tell you is the shape that molecule has. Does that make sense? It tells you which atoms are bonded to which. All right? It tells you that oxygen has a bond to two different hydrogens, but it does not tell you the three-dimensional shape of the molecule. All right? And that is why all of these are correct, because Lewis structures don't describe the shape of the molecule. All right? That's what our next topic is going to do. And our next concept, the next topic in this course, is something called VSEPR theory. Oops. I just drew that in the wrong layer. All right, VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion. All right, that is the VSEPR. All right, that's the VSEPR in VSEPR theory. All right, valence shell electron pair repulsion. Now, what does that mean? Great question. I'm also doing some product placement for Snapple. I'm not actually. That was free, Snapple. You're welcome. So valence shell electron pair repulsion theory. What are we talking about? This whole theory has a very simple premise, all right? And that premise is that like charges repel, like charges repel each other, electrons are all negative i.e. they repel each other. All right. And so because like charges repel each other and all electrons have negative charges, have the same charge, they're going to want to get to as far away from every other group of electrons as possible. All right. So I should say because of these two, each bond and lone pair around a central atom will try to get as far away from each other bond / lone pair as physically possible. All right, and that is the central idea behind VSEPR theory. Every single bond and lone pair around your central atom is going to try to move to be as far away from every other bond and lone pair as physically possible because they are all made up of electrons and they're all repelling each other. All right, that's the idea behind VSEPR, and we're going to use this idea to start discussing what actual shape molecules will have in three-dimensional space. All right. So that's where we're headed. Now we need to talk a little bit about just some kind of vocabulary and nomenclature that's used in VSEPR theory, so we're all on the same page. All right, so first off is so let's talk about just some terminology. First, we need to talk about electron groups. All right, so electron groups. One lone pair around your central atom equals one electron group. All right. One single bond is also one electron group. One double bond is one electron group. And one triple bond in VSEPR theory is also considered one group of electrons, all right? One electron group. The reason for this is you might be going like, okay, lone pair being one group makes sense. Single bond makes sense. Shouldn't a double bond be more than one electron group? And the answer is no. So if you consider, for example, oops, hang on. So this is a molecule of carbonate, charged for -2. If I asked you, how many electron groups are around carbon, the answer is going to be 3. All right? Because this is group number 1. This is group number 2. And this bond is group number 3. Now, you might be going, well, but should the double bond count for, well, double? The answer is no. It shouldn't count for double, and here's why. Even though there are 2 bonds there, that carbon-oxygen double bond, there are 4 electrons in it, but they're all smushed into the same place. They're all smushed into the zone between this oxygen and this carbon. So since they're all sandwiched into the same place, they're one group of electrons. Does that make sense? So a double bond is one group, a single bond is one group, a triple bond is one group, because they're all, even though there's more in a double or a triple, they're all in the same space, so they're grouped together. All right? So another way of looking at electron groups is you could say that the number of electron groups around your central atom is equal to the number of lone pairs plus the number of atoms attached. All right, that is the number of electron groups around your central atom. All right. An LP, just so that we're on the same page, that's just shorthand for a lone pair of electrons, i.e., if you looked at the Lewis structure for water, for example, that is a lone pair. All right. 2 more vocabulary words, and then we're ready to start actually getting into and applying VSEPR theory. There's something called an electronic geometry. All right, the electronic geometry is the shape that all electron groups make around the central atom. And then there's something called the molecular geometry. And the molecular geometry is the shape that the atoms make around the central atom. All right, so electronic geometry is the shape all electron groups make around the central atom. The molecular geometry is just the shape that the atoms make around the central atom. All right. Now, so this is kind of the foundation. This is some vocabulary. These are the tools that we're going to use to, these are kind of the tools, the pieces, the gears of VSEPR theory that we're going to use now to learn what VSEPR theory tells us about the shape of molecules and actually start labeling what are called molecular geometries. All right. So, let's talk about, so let's go ahead and start with, actually, so we've got the Lewis structure, electron groups, lone pairs, electronic geometry, molecular geometry, and then the three-dimensional shape. All right, so got electron groups. Go with electronic geometry. Lone pairs connected to molecular geometry. We're starting with a Lewis structure. We're ending with a three-dimensional structure. All right. So let's go ahead and start with carbon dioxide. That's not the Lewis structure of carbon dioxide. That is the molecular formula. The Lewis structure for CO2 looks like this, and actually, I'm gonna give myself a little more room to work with. All right. Here's our Lewis structure for carbon dioxide. Now, to determine, so with VSEPR theory, we are going to look at, actually, sorry, I need to add something here. Something I forgot. Three-dimensional structure and something called a bond angle. That's where we're headed. Okay, so to determine what the three-dimensional structure is, what the shape this molecule has, the first thing you need to do is determine how many electron groups you're dealing with. And when you look at carbon, carbon has, I'm going to do this in black actually. Attached to our central atom, we have two atoms, 0 lone pairs. So 2 plus 0 means we have 2 electron groups. all right? 2 electron groups. We've already said this, but there are 0 lone pairs. Now, something that's very important that you need to keep in mind. Because you might look at the molecule of CO2 and think, I see 4 lone pairs. When we're talking about lone pairs in VSEPR theory, we're talking about lone pairs that are on the central atom. All right, we are only concerned with lone pairs on the central atom. If they're not on the central atom, they're not going to affect the geometry of the molecule. So that's why we say 0 lone pairs, because carbon, our central atom, has no lone pairs. All right, now, what determines the electronic geometry are the number of electron groups around the central atom. All right? When your electronic geometry is 2, your electronic geometry is linear. All right? So that's something worth noting. Two electron groups equals linear electronic geometry. All right, so 2 electron groups, linear electronic geometry. And then the second thing, this is a special case, but it's true. When you have 0 lone pairs, your molecular geometry and your electronic geometry are the same, all right? That's the second thing about this example. That's a little bit of a special case. 0 lone pairs sorry, I forgot to silence my cell phone. When you have 0 lone pairs, that means that your electronic geometry will equal your molecular geometry. So that's another thing to keep in mind. So because we have no lone pairs, that's what makes these 2 equal. All right. Now, since we only have 2 groups around our central atom, what is the farthest 2 groups can get in 3-dimensional space? The answer is 180 degrees. The farthest these 2 electron groups can get from each other in 3-dimensional space is 180 degrees. So for carbon dioxide, this is the 3-dimensional structure. All right, the 3D representation of carbon dioxide is just a straight line with the 2 oxygens on opposite ends of the carbon. You might be looking at this and going, well, Josh, that looks exactly like the Lewis structure. It's a coincidence. That's not always the case. In fact, it's rarely the case, as you'll see with our next example. All right. But we have a 180-degree bond angle. That's a three-dimensional structure for a linear molecular geometry. Let's use this VSEPR analysis to look at a molecule of formaldehyde. So this is formaldehyde. That's the Lewis structure for it. The first question we need to answer is how many electron groups are around our central atom. And when you look at the number of electron groups around carbon, there are 3 atoms, 0 lone pairs. Again, 0 lone pairs directly on carbon. So there are 3 electron groups. All right, we've got 3 electron groups. As far as our lone pair numbers are concerned, we've got 0 on carbon, and we know that 0 lone pairs means that our electronic geometry and our molecular geometry will be the same. When you got no lone pairs on your central, they're the same. And the reason for that, remember, electronic geometry is the shape that all electron groups make. Molecular geometry is the shape that all atoms make around the central atom. Now, if you have no lone pairs in your electron groups, of course they have to be the same. Once you do start having lone pairs around your central atom, that will change the molecular geometry. All right, we'll get there in the next example. First, 3 electron groups. Now, when you think about it, okay, so the name, when you have 3 electron groups, your electronic geometry is trigonal planar. All right, trigonal planar. And as we said, because we have no lone pairs, our molecular geometry is the same. All right, now let's draw this thing. Let's think about how far Yes. Yes, that is correct. Totally, Ariana. It's 3 electron groups because there are 3 groups of electrons around the central atom carbon. Another way to look at that is we've got 3 groups of electrons because we have one oxygen and 2 hydrogens attached. So that's a total of 3. Totally. Great question, by the way. Okay, now let's think about, so we have these 3 atoms, these 3 groups. Let's think about the farthest away they can possibly get from each other in space. All right. Now, move this C down just a little bit. The farthest away that 3 groups can get from each other, all attached at a central atom, is 120 degrees. That's as far as they can get from each other in space. So this is the 3-dimensional representation of this molecule. And you'll notice it looks different than the Lewis structure. In the Lewis structure, there are two 90-degree right angles and then one 180-degree angle. And that is not the case here. The actual three-dimensional structure of this molecule has everything evenly distributed. There are three 120-degree angles. So this is actually the shape the molecule has. This is the actual three-dimensional shape of our molecule. And this is what every trigonal planar geometry looks like. Every trigonal planar geometry has 120-degree bond angles. Every trigonal planar geometry will look like this. Okay. Let's see what happens once we introduce a lone pair to our central atom. And we'll do this by using this VSEPR analysis on a molecule of nitrite. Nitrite is NO2. If you draw its Lewis structure, it'll come out looking like this. I need a little more room here. Nitrite is an ion, so got to throw a bracket around this dude. Okay, let's take a look. So, oh, hang on. There we go. Let's look at the number of electron groups around our central atom. Our central atom's nitrogen. There are two atoms attached to nitrogen and one lone pair. So you add these two together. And we find that we get 3 electron groups. All right, 3 electron groups. But you'll notice that one of those groups is a lone pair. All right, one of those groups is a lone pair. This doesn't affect our electronic geometry. Every time you have 3 electron groups around your central atom, your electronic geometry will always be trigonal planar. All right, your electronic geometry will always be trigonal planar. The question is, how does this affect our molecular geometry? And that is what we're going to find out. First, let's go ahead and draw the trigonal planar scaffold. So we have nitrogen in the center. And now we know we're going to have 3 groups around our central atom, and they're going to be spread evenly apart. They're all going to be 120 degrees apart. The difference is now one of these 3 groups is a lone pair. We have a double bond to one of these oxygens, and then a single bond to the other. And I'm still putting a bracket around the entire thing. So Carolina, one oxygen has 2 lone pairs and the other oxygen has 3 lone pairs, just like in the Lewis structure. Something to remember. Remember, 1 lone pair equals 2 dots. So when we're talking about lone pairs, this is 1 lone pair. This would be 2 lone pairs. This would be 1, 2, 3 lone pairs. So you can see that in the when we drew out the electronic geometry, this oxygen has 1, 2, 3 lone pairs. This oxygen has 2 lone pairs. And then our nitrogen, our central atom, only has 1 lone pair. Yes, exactly. Lone pairs are pairs of electrons that are not used to make bonds to other atoms. They're just hanging out around that one atom, fulfilling its octet. Okay, whoops. Oh no. Oh, I did that all over. I thought I did it in a fresh layer. Okay. I'm going to need to reconstruct this page just a little bit. Blake, that is correct. The molecular geometry is trigonal planar because whenever you have 3 electron groups, your molecular geometry will always be trigonal planar. Because trigonal planar is the shape the molecule makes when, sorry, the shape of the molecule, including all of the electron groups. Molecular geometry only looks at the shape of the atoms, all right? So when it comes to, totally. Now, when it comes to drawing the molecular geometry, you draw the molecule exactly the same you did for the electronic geometry with one twist. You do not draw the lone pair on your central atom as its own independent group. For the molecular geometry, you just draw it as a pair of dots on your central atom. And when you look at the molecular geometry here, you can see that it kind of looks like a straight line that got bent. All right, you can see that it looks like if you put a kink in a straw. And that's because the molecular geometry for this molecule is just that. It's a bent geometry. Whenever you have 3 electron groups and 1 lone pair, your molecular geometry is bent. All right, so this has a bent molecular geometry. Now, what about our bond angles? Our bond angles are determined always by our electronic geometry So because they are bond angles of 120 degrees in our electronic geometry, they are 120 degrees in the molecular geometry as well. All right, so this is the three-dimensional shape, the molecular geometry. For nitrite, bond angles of 120, molecular geometry is bent. All right. So we've done one example with 2 electron groups. We've done two examples with 3 electron groups. What happens when we get 4 electron groups in play? We'll cross that bridge. We'll look at that with the consideration for a molecule of methane, or carbon tetrahedride, as we would call it in this class. All right, so CH4. Now, let's start by looking at the electron groups around our central atom. We have 4 atoms attached to carbon, 0 lone pairs. So we have 4 plus 0, or 4 electron groups. 4 electron groups. Now, whenever you have 4 electron groups, your electronic geometry will always be something called tetrahedral. All right, and we know that we have 0 lone pairs, and whenever you have 0 lone pairs, your molecular geometry is the same as your electronic geometry. All right, so these two are equal. Now, what does a tetrahedral molecule look like? I'm so glad you asked. It takes a little bit to visualize. So, I'm going to draw the molecule, and then I'm going to explain it. All right, here's what a tetrahedron looks like. Now, just so you know, well, here, I'm going to draw the H's. Now, what are we looking at? All right, here's what we're looking at. When we're using VSEPR theory, when we're drawing three-dimensional depictions of molecules, straight lines like this, these are in plane. Always go with your gut, never change your answers. I'm a horrible speller. I wrote it right the first time, then I'm like, I should change it. No, in plane. So these are in the plane of the screen, all right? They're flat, they're vertical. On your paper, that means they're in the plane of the page, all right? The wedge this is popping out. So that wedge represents not something that's like flat in plane, but something that's like my pen that's popping out at you. That's what that wedge is. And then the dash, this dashed line is a bond that is going back going behind and away. All right, is so the wedge was pop coming out at you. The dashed line is coming back at me away from you. All right, so that's what these bonds mean. Straight, flat bonds are in the plane of the page or the screen. Wedges are popping out at you. Dashes are popping back, going back at me behind the screen or the page. All right, so this is the tetrahedral geometry, and the bond angles here, the farthest that four groups can get away from each other in three-dimensional space, is 109 degrees, and that is the bond angle. Doesn't matter which you pick. Any two hydrogens will form a bond angle of 109 degrees. Nope. So Rox just asked the question: are the number of dashes equal to the a representation of the number of atoms? And they're not. The number of dashes just represent one single bond that is moving back away behind the screen. So it's indicating the direction that the bond is pointing, and that's it. The number of dashes in that thing does not signify anything. All right, so our bond angles are 109 degrees. This is where those of you who actually play D&D will have an advantage over the rest of the class. If you've handled a D4, which is what you roll for like healing potions, also some low-grade weapons, roll a D4 damage. The D4 shape is the shape that each one of these H's make. Each one of these H's would be at the vertex of that D4. So if you play D&D, now you know. It's the first time that, or maybe not the first time being nerdy has paid off, but so Ariana, great question. So Ariana just asked a great question. How do we figure out the degrees, right? With linear, we could kind of we knew that, right? Like two things getting completely opposite from each other, that's 180. Three things, okay, a circle's 360 degrees divided by 3, that's going to be 120. How do we get this 109? You have to be really, really good with geometry and your shapes to be able to determine that off the top of your head. I would recommend writing all of this stuff down on your exam sheet. All the stuff that we've covered, all the stuff from the VSEPR lecture, so that you can have it for a reference. Because when you're doing VSEPR problems on an exam, during an exam, you want to be able to like look at a structure and go, okay, let's see here. 4 electron groups, 0 lone pairs. That means that we're tetrahedral and our bond angles are 109. You just want that as a quick reference. If we were doing this like normal, if we were meeting in a classroom, I would tell you that you'd have to memorize this stuff, but because we're not, because you have an exam sheet, you don't have to memorize it. But if you're not going to memorize it, you definitely want it for quick reference. Totally. And I guess the ultimate answer to your question is, how do you know the degrees? Because I'm telling you. But I wouldn't ask you to figure that out on your own. That's an advanced geometry class, which is not the one I'm teaching, and it's not the one you're taking, so you don't have to worry about some weird calculation. All right. So that is the tetrahedral electronic geometry with 0 lone pairs. Let's take a look at what will happen when we start adding lone pairs and how that will change, how that will affect our molecular geometry. All right. Let's look at a molecule of ammonia. Ammonia is NH3. All right. Now, we got to start by looking at our electron groups. We have 3 atoms attached to our central atom, and we have 1 lone pair. So that means we have a total of 4 electron groups. All right. Anytime you have 4 electron groups, your electronic geometry will always be tetrahedral. All right, our electronic geometry is tetrahedral, but our molecular geometry is going to be something different. We know it will be different because we don't have 0 lone pairs. The only time they're the same is when you got no lone pairs on your central atom. In this molecule, we do have a lone pair on our central. So to get to our molecular geometry and that 3-dimensional shape, we start by drawing the tetrahedral electronic geometry. Now, every tetrahedron is the same. You do 2 groups in the plane of the page, 1 wedge coming out at you, and 1 dash going back towards me, away from you. Excuse me. Now, it doesn't matter where you put your H's and your lone pairs. I'm going to put my hydrogens there and my lone pair there because I think it's easiest to see. All right. Now, once you have your electronic geometry drawn out, the way you get to your molecular geometry is you need to take your lone pair and go, okay, I'm not going to draw that as its own independent group. I'm going to draw everything else the same. All the other atoms are the same. But I'm not going to draw my lone pair as its own independent group. And that gets you to the molecular geometry. Now, this molecular geometry, and it's a little hard to see, but basically what we have is we have like these, my 2 fingers and my thumb are where the hydrogens are, and then the nitrogen is like right there, all right? So it kind of makes, if you're looking at the base, it would look like this, a pyramid shape with 3 vertices in the on the base, all right? So it's like a pyramid with 3 points on its base. So the molecular geometry, when you have 4 electron groups and 1 lone pair on your central atom, is trigonal pyramidal. All right, trigonal pyramidal. That is your molecular geometry. Your bond angles here are still 109 because whenever you have an electronic geometry that's tetrahedral, that determines your bond angle. So we're still dealing with 109-degree bond angles, including this one back here. All of them are the same. But the molecular geometry is trigonal pyramidal. All right. Let's see what happens once we get two lone pairs in play. And for this final VSEPR example, we're going to look at water. And this discussion where we began it. So, first let's look at our electron groups. We have two atoms attached to our central atom, and we have two lone pairs attached to our central. That leaves us with 4 electron groups. All right, 4 electron groups, 2 of which are lone pairs. Now, whenever you have 4 electron groups, your electronic geometry will be tetrahedral. They will be tetrahedral. So let's go ahead and start by drawing that out. Doesn't matter where you put your H's or your lone pairs. I think this will be easiest to see if you put both of your H's on your lines and then you put your lone pairs on your dashes and your wedges, but it's correct no matter what. All right, now for our molecular geometry, you draw everything exactly the same, but you take your lone pairs and they're not represented in the shape of the molecule. So for our molecular geometry, our lone pairs are just drawn as dots. All right, so here's our molecular geometry. And once again, you might be looking at this and you might be thinking, well, wait a minute, this kind of looks like a bent line, like someone put a kink in that straw. And it does. And our molecular geometry is bent. Just like when you had a trigonal planar geometry with one lone pair. You might be going, that's confusing. How do you know the difference then between a bent tetrahedral situation versus a bent trigonal planar? And the answer is the bond angle. Because a tetrahedral electronic geometry, a molecule with a tetrahedral electronic geometry, will have bond angles of 109. But a bent trigonal planar geometry will have bond angles of 120. So that bond angle comes in clutch. Is super important for determining one way or another. All right. Okay, so I'm looking at what comes next, and I feel like this is a good place to stop. So we've covered all of the VSEPR theory that we're going to cover in this course. If you want some practice, you can maybe try working a few of these. So label the molecular geometry and bond angle for, all right, and I'm going to give you a few molecules. So you can try this on your own, but then we'll go ahead and stop. So here. So label the electronic geometry and bond angles for the following molecules. So that's a good one. Let's do CFCl3. Sorry, no, CFCH3. There we go. Let's do let's do these three. So we'll call this A, B, and C. So go ahead and try these on your own. There's more practice in the book, in the homework. But we'll go ahead and call it a night here. We almost finished chapter 4. We'll wrap it up on Thursday and then dive into chapter 5. Alrighty. I'm going to go and I will see some of you the second half of section 60 for oral exams starting at 7. Later, dudes.